Let's discuss in this video how to compute 2D and 3D moments of inertia. So a good example of a 3D object would be an object that looks like the stop. You can see that it approximately resembles a cone. So we will be finding the moment of inertia of a cone in this video. 2D objects, well, there's no such thing as a 2D object because every object has some thickness, even if it's one atom thick. But I'm thinking of a 2D object as an object that has the same thickness throughout. If it has the same thickness throughout, then its mass is proportional to its area. So I'm thinking of things like this triangular piece or this circular disc. A 2D object of this type is called a lamina. And so we're going to be also looking at how to compute the moment of inertia of laminas. So let me first lay out the general philosophy of our approach and then do the specific examples of a triangle and a cone as illustrations of the general method. So the general principle is as follows. I have here, and this works for 2D or 3D. I'll explain how. So some x-axis and y-axis. And let's suppose I'm given the graph of a function. So this could be some function of x. Now, if I want to make it a 2D object, I'm also going to consider cases which are pretty symmetric. So a 2D object would be a completion of this in both directions, but it's flat. So if I'm considering this to be a 2D object, then I would look at an element, and I'm rotating about the x-axis, so it's going to be this type of rotation. So the element I have here is basically a rod. Okay, you can see this little element would behave like a rod, pivoted about its middle. So this is called a rod element. This is dx. That would be y. So it's y upstairs and y downstairs. So it's going to be 2 times y. And so the area for this 2D object is going to be 2y times dx, where y is the function of x. And for the conversion of area into mass, I'm going to use what's called a two-dimensional mass density. This density can change from place to place, or it can be constant. I'm only going to consider the constant case here. So let's assume that the density is sigma naught, meaning that it does not change from place to place. And that's given by dm over dA. So the mass element dm is equal to sigma naught times dA. So that's going to be 2 sigma naught y dx, where y is a function of x. That's the basic setup for a two-dimensional object. A three-dimensional object is no different. I'm going to assume that the three-dimensional object is got by revolving this about the x-axis, so it would be a solid of revolution. For example, I can get this conical top by taking a triangle and revolving it about the x-axis. So I'll try drawing that shape again, but this time I'm revolving it so it looks more like a bell. The mass elements are no longer strips, but they have to be considered as disks. The disks have the same width dx, and the radius of the disk is now what used to be the height of the strip. Let's write down the volume of this disk. The volume is given by the area times the thickness. And the appropriate density to use in case of volumes is rho naught, defined as dm over dv. So from this I can get my mass element dm, it's rho naught times dv, so that's pi rho naught y squared, and I'm going to assume that the y is again some function of x. So that's a function of x, and that's rotated to get this bell-shaped curve figure. So that's f squared of x dx. So that's the basic setup, and that gives you the mass elements. Now for the moments of inertia, we're going to consider the moment of inertia of this 2D object. It definitely resembles a rod pivoted about the center, and if you look at your moment of inertia table, the moment of inertia of a rod pivoted about its center is 1/12 ml squared. So I'm going to use the mass element di for this to be 1/12 dm, and the length of the rod is 2y squared. What about the, let's write down what this is. It's going to be 1/3 dm times y squared. So if I substitute for dm, that's going to be 1/3. dm is already 2 sigma naught f of x, y is f of x, so that's going to be 2 sigma naught f of x cubed, because there's f of x coming from here and that y is f of x, so it's going to be f of x cubed dx. And here I'm going to get a similar expression, but let's find out what the 3D moment of inertia di for this element would look like. Well, that element most closely resembles a disk. Imagine that's very thin. So it's going to be 1/2 dm times the radius squared, the radius being y. So I can put down what dm is now. It's this one. So it's going to be 1/2 times pi times rho naught. That's f squared here, and y is also a function of x, so that's going to be f squared there, so that's f to the 4 as a function of x dx. So these two procedures give us the incremental moment of inertia of each element, and the total moment of inertia is simply got by integrating from 0 to the full extent of the object, whatever that length or dimension is. I'll call this the height of the object. So the moment of inertia, the full moment of inertia, is just the integral from 0 to h of di. And that's the moment of inertia for the 3D object is the same way, 0 to h of di. So this procedure gives you the moment of inertia of any 2D and 3D object regardless of its shape. So if I were given a function that describes the shape of this top, I could find its moment of inertia exactly. Let us try to work this out for the triangle and the cone. So you'll see that these are very simple applications of the general principle. I hopefully will have an easy way of determining what the function of x is for the triangle. Let's say that the triangle has got height from 0 to h, and let's call this half the base I'm going to call r. So to find the equation that describes this triangle, the best way to proceed is to look at similar triangles. So I'm going to look at this little triangle. So if I look at that, I have tan theta equals y over x. But if I look at the big triangle, tan theta is also r over h. So now I have y as a function of x. Y is just going to be r over h times x. And now I can plug it into my formula. So the moment of inertia I is just going to be 2/3 sigma naught. I'll take the 2/3 and sigma naught outside because they're just constants. And now I have to cube f. If I cube f, I'm going to get r cubed over h cubed, which will also come outside. And then I'm left with x cubed dx from 0 to h. So that's going to be 2/3 times sigma naught r cubed over h cubed times h to the 4 over 4 when I integrate. So that gives me 1/6 sigma naught r cubed h. Now that doesn't quite put it in terms of the mass. So to put it in terms of the mass, let me also find the total mass of this object. The mass of the object is the integral of dm. Now for dm, I have 2 sigma naught that come outside the integral sign times the integral of f of x, which has got r over h. So I'll bring that outside as well. And so that's going to be just x dx from 0 to h. That's 2 sigma naught r upon h. This is x squared over 2. So that's going to be h squared over 2 when you integrate it between the limits. And I'm going to get sigma naught r times h. So that's the mass. Let me try to express this in terms of the mass. So that gives me 1/6. I can take out sigma naught r times h and multiply the whole thing by r squared. That's the same as what I have above. So that's be 1/6 mr squared. That's our answer. It is not a standard result and it's not found in any tables, but now you know what it is. Let's apply the same logic to a cone next. That will be the 3D example, and for the cone we'll follow the protocol laid out here. There's almost no difference between the setup for the cone and the triangle in terms of the equations involved. The equation of this, if I call the height of the cone h and the radius of the cone r, that was one of my motivations to keep these symbols the same so I can save myself the trouble. So this equation is just that. And now all I would have to do is substitute it into my template. So let me carry it out. The moment of inertia I, from this, I can take pi over 2 rho naught outside. that's the function of x here. When I do that to the fourth power, I'm going to get r to the 4 over h to the 4 outside, leaving me with just x to the 4 inside, the integral sign from 0 to h. So that can be integrated. It's pi over 2 rho naught r to the 4 over h to the 4 times h to the 5 over 5. So that gives me pi over 10 rho naught r to the 4 times h. Again, that's a strange looking result, and we would like to write everything in terms of mass to make it look like a standard moment of inertia table entry. So the mass is going to be the integral of dm, which is that. So when I take the integral, the pi comes outside, the rho naught comes outside. I have an f squared. Well, f squared involves r squared over h squared, which I can also take outside. And then I just have x squared dx from 0 up to h. Let me at least draw the element here. So same as that. Let's evaluate this. That's going to be pi rho naught r squared over h squared. The integral of x squared is x cubed over 3, so that's going to be h cubed over 3. So this is 1/3 pi rho naught r squared h. If I want to write the moment of inertia in terms of the mass, you'll notice that I don't have a 3. So what I'll do is I'll create it by writing this result as 3 over 3 times pi 10th rho naught r squared h times r squared. I'm writing r to the 4 as r squared times r squared. And now I'm going to trade places. I'm going to take the 10 outside and the 3 inside. When I trade places, pi over 3 rho naught r squared h is precisely the mass. So that's going to be 3/10 mr squared. Is that the right result? Well, let's check. Indeed, it is the right result for the moment of inertia of a cone about the central axis. So I've described not only how to do the moment of inertia for a cone and a triangle, but you can use this method for any of these objects that you find here. The same tricks will hold.